Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be developing an introduction to evolutionary game theory. My name is Rick and my co-teacher, who originally prepared these notes, is Christoph. So our goal today is to develop kind of the mathematical foundation of evolutionary game theory. We'll be doing that by starting with a simple population model. Then we'll extend that to an evolutionary model. Then we'll explore how you can solve these models, solve the dynamics with two simple methods, by finding the equilibria and their stabilities. And once we've got that, we can develop it into a full evolutionary game theoretic model. And finally, we'll talk about the replicator equation. And that's kind of our end goal, is to get to the replicator equation. And so we're going to do this by taking these kind of simple steps. We'll start with a very simple model and then throw in a couple elements. Throw in evolution and then throw in game theory to get to that point. So let's start with that simple population model. The idea here is that we consider a population of individuals, of replicating individuals. Let's call them A. So A will be a symbol that represents one of these individuals. To keep things as simple as possible, let's say we have just one species we're interested in. Let's make it asexual and haploid, and basically it's just going to be a clonal reproduction. So A's beget more A's. So there's not a lot interesting going on there. The only thing that we might really keep track of here is the population size. And we might denote that by, let's say, little a as a function of t, time. And how that changes is going to depend on the fitness of the population. And we'll just use a parameter to describe that. Let's call it f sub a. There's all sorts of ways we could write a model that has all these properties. We're going to consider a very simple case, which is just exponential growth or decline. And what I mean by that is the population size changes over time. The rate of change is equal to that fitness times the population size itself. And when you have a model that exhibits that kind of property, then the solution, if you'll remember back to your first year calculus, is that the population size A of t is equal to whatever it was at time 0 times e to the power of f sub a times t. And that's an exponential model. So it's always good to check that the solution that you think you have is actually a correct solution. Let's do that. If a is this thing, then we can just take the derivative of it to get dA dt. And if you do that, you should see that it becomes a naught times fa times e to the fat. And you should notice then that the a naught times e to the power of fat is just a of t again. So this whole equation becomes fa times a, which is exactly what we had in the first place. So we have confirmed our result. So this is a very simple kind of model. Let's just go over very quickly what can happen in the long run. So what happens will depend on the parameter fa. If fa is positive, then we get a population explosion, and a of t grows to infinity. If fa is exactly 0, which would be a little bit weird, then we would get a constant population size, so that a of t just stays at whatever it was at time 0. Now, this case here is a little bit odd, because it's unlikely that fa would be exactly 0. But if it did happen, then in a real population, you'd expect that other forces would come to dominate, just random events. And so you might expect to see drift in this case. So it might not stay at a naught. It might drift, the population might drift to higher numbers or lower numbers, but there's no pull like there is when fa isn't 0. And finally, let's look at the third case. If the fitness is less than 0, then we'll get eventual extinction, because a of t will decline steadily towards 0. So let me just draw those cases in a little picture. So if FA is bigger than 0, then the population is going to grow and start accelerating upwards. That's if FA is bigger than 0. If FA is exactly 0, then we'll just stay at a constant population size, or drift. And if the if the fitness is less than 0, then we expect our population size to drop, but never hit 0, except due to random events. Okay, so let me just associate these things. So this case here is that case, and the last case is the bottom case here. So the last thing that I want you to notice about this model is that it's just about ecology, about population numbers, or we could say it's about population size. It doesn't say anything about selection, which types are being selected for or selected against. So it's not an evolutionary model. But we can extend the model to make it evolutionary. And one of the criteria we have then is that we need it to be about frequencies of traits in a population. So you might imagine Darwin's finches or something, and maybe it's the size of their beaks could be the trait that we're interested in. So we need variation in that trait, and we want to watch the change in frequency of that variation. So what we need to add to our model is a second type. So let's imagine the simplest case we can have with a heritable trait and some variation in that trait. Let's say we have a single gene that we're following, and there are just 2 alleles for that gene, or we can say there are just 2 types. So now, instead of just individuals that are A's, we could also have individuals that are B's, and maybe they carry the B allele and the other individuals carry the A allele. There's still just one species, and we're interested in the changes now. We want to track the numbers of both of these types. Before we had A of T was our population size. Now we need to keep track of that and the size of the other population, B of T, and together they make up our whole population. For this to be an evolutionary model, we also need some selection acting on these different types. So instead of just the constant FA, we now have FA for type A individuals, that's their fitness, and type B individuals have fitness FB. And let's use the same simple exponential model. So the rate of change of the population size of type A is equal to FA times the population size, and dB dt is equal to FB times that population size, B. So again, that's exponential growth or decline, depending on what those parameters FA and FB are. What's important to us is not the population sizes themselves, but the frequencies of these types. And for frequency, I just mean the proportion of the population that is of each type. So for frequency, we could look at X, which is the number of A's divided by the total population size, or the remainder, which just has to be the number of B's divided by the total population size. Okay, and this term frequency, we're going to come across that again and again, so keep that in your mind. When we're talking about frequency of types in a population, we mean proportion. What fraction of the individuals are this type or that type? So if we want to know what happens to the frequency, we need to apply the quotient rule to take the derivative of this and solve for it in terms of the derivatives of A and B. Okay, so do you remember how to do the quotient rule? First, we take the derivative of the numerator and multiply it by the denominator, and then it's minus the numerator times the derivative of the denominator. And all of that is divided by the square of the denominator. And we can simplify that a little bit. We still have 1 over a plus b squared, but the numerator is a little bit simpler because we have a times dA dt occurring in two places, here and here. So they cancel each other out and leave us with just this. And we can further simplify that because we know what dA dt and dB dt are. So the first term in the brackets is B times FA times A, because that's what dA dt was. And the second term is A times dB dt, which is FB times B. And I'm just going to rewrite that in a slightly different way. You'll notice that there's an A and a B and another A and another B in the brackets. So those can come out because they factor out of the brackets. And we can write that as A over A plus B times B over A plus B. I'm just using those A plus B's from the denominator, and all of that times FA minus FB. Why did I do that? Because we have this expression already and this one already. They're just up here. X is equal to A plus B, A divided by A plus B, and B divided by A plus B, that's just 1 minus X. So we can make this equation even simpler. It's X times 1 minus X times F sub A minus F sub B. And that's how the frequency of A types changes over time. So now we've got an equation for the rate of change of this frequency that doesn't even depend on the population size. It only depends on itself, X, and the parameters FA and FB. Now we want to use that information to try and figure out what's actually happening to X and how it depends on these parameters. So we want to solve the dynamics, and we'll use two simple techniques to do this. The first is just solving for where the equilibria are. I'm using the term equilibrium. I don't mean a Nash equilibrium. I just mean a place where X is not changing. So our motivation for doing this is that we're interested in the long-term trends, or in other words, what eventually happens to the population. And the technique we're going to use is to look at the equilibria, and the equilibria are special values where X doesn't change. You should keep in mind what the term equilibria or equilibrium means, and take note that we're not using it in the context of Nash equilibria. It's a slightly, an important difference between those concepts. So we want to know, when is it that dx dt is equal to 0, so X doesn't change? Well, this form of the equation is really handy to figure that out, because dx dt can be equal to 0 when three things are true. Either this first factor is 0, or the second factor is 0, or the third factor is 0. So the first case is just if X is equal to 0. And the second case is just if 1 minus X is equal to 0, or X is equal to 1. And to summarize that, if we lose all of the A types, so the frequency of A is 0, or we lose all of the B's, which means the frequency of X is equal to 1, or all of them, then the population is all one type. We have no variation in our population anymore, so there's no room for evolution to work. There's also the third case in our rate equation. That's if FA is equal to FB. That also gives dx dt equal to 0. And the interesting thing about that is that's for all X. It's always 0. But the less interesting thing about that is that it's unlikely to occur by chance if these parameters FA and FB are arbitrary constants. Maybe not arbitrary, maybe, determined by experiment or something like that. But in any case, if you go out and you try just measure two values of parameters, you get FA and FB, it would be a really weird thing if they happen to come out to be exactly equal to each other. So we don't expect that to occur very often. A little bit further on, we're going to actually explore this special case in more detail, and we'll get into why later on. Okay, now the second technique we're going to use to help us solve the dynamics and understand what's going on is to look at the stability around the equilibria. So we already saw that the limiting frequencies, x equals 0 and x equals 1, they're equilibria. The population doesn't change in structure anymore. But what about in between? So we're interested in what happens for all x in the range from 0 to 1. So let's look at two cases. If FA is bigger than FB, and on the other hand, if FA is smaller than FB. And to see what's going on, let's draw dx dt as a function of x itself. So I'm imagining x is increasing to the right in each of these cases, and the left boundary is x equals 0, the right boundary is x equals 1, and we're interested in dx dt in these cases. So recall that our equation for dx dt is equal to x times 1 minus x times fa minus fb. Now, if fa is bigger than fb, then this third factor is positive. That means that we have a quadratic, because there's an x factor here and an x factor here, which opens downward because of the minus sign in front of this x here. You can check this for yourself. You can plot it, plug in some values of fa and fb, even if it's just a value of fa equals 1 and fb equals 0. Then plot this, and you will see that dx dt does something like it increases, and then it's going to level out, and then it's going to decrease. It doesn't have to level out in the middle. It can be anywhere between them, but it does have to pass through 0 at x equals 0 and 0 again at x equals 1. On the other hand, if fa is less than fb, I think you can guess what happens. It's again a quadratic, so you get a parabola. But now it has to open upwards. So now again it starts at 0 and it increases, it decreases at first and then it increases. And again it crosses through 0, 0. And another way to see that is if x is bigger than 0, then this factor is positive. If x is less than 1, then this factor is positive. So the sign of dx dt is just equal to the sign of fa minus fb. So if this is positive, then dx dt is positive. If this is negative, then dx dt is negative. So this is going to help us figure out the stability of the system. Because if we know that dx dt is positive, that means that wherever it's positive, x is increasing over time. It's like saying x has a positive speed, so it's moving forward. So x is going to increase. And if x is increasing, then wherever we start, whether it's there or there, it's going to move to the right. And that's true for anywhere where dx dt is positive. So it's true all the way up to here where it hits 0 again, and all the way from here. So no matter where we are in between, it's always increasing to the right. And what about the other case? Now we know dx dt is always negative, so x is shrinking. So we're approaching x equals 0. So anywhere in between, we'll see that we're moving towards the left, towards x equals 0. So as long as dx dt is positive, then we move to the right to increasing x. If dx dt is negative, then we move to the left towards smaller x. And that's a general rule that you should keep in mind. And knowing that, we can say something about the equilibria. Let's label our equilibria. So we'll call that a filled dot, a stable equilibrium. And an open circle will be an unstable equilibrium. And what we mean by stability here is that if we start at one of these equilibria, and we're knocked away from it, just a little bit to the left or to the right, will we return? Will the system dynamics return us to the equilibrium, or move us further away from that equilibrium? And I think you can see here, the trend is always to the increasing x to the right. So if we get knocked out of this point, let's say to here, then the dynamics are going to pull us further and further away. So we're not going to return. And this is an unstable equilibrium. On the other hand here, if we get knocked away from this equilibrium, let's say we get moved over here, then we're going to get pushed back to it. So that is a stable equilibrium. And I think you can figure out the other one. You should find that this is a stable equilibrium and this is not. It's unstable. So again, the criteria there was that a stable equilibrium, we will return if we get disturbed away from it. On the other hand, for an unstable equilibrium, we won't return if we're disturbed. The concept of stability and knowing what stable and unstable mean is important, and we're going to use it repeatedly in the remainder of the course, so make sure you understand it. Okay, so we've come a long ways. We've started with the simple population model, then we added evolution, and we've got this moderately interesting evolutionary model, but there's still no game theory in it. There's no games going on. So let's add that now to create a full evolutionary game theoretic model. So the question that arises is, where are the games in this model? And we can embed the games in the fitness of the individuals. You might say they were hidden there all the time. So a game will result if we make the fitness depend on the interactions with others. So instead of having a strictly constant fitness, the fitness of any one individual depends on the interactions it has with other individuals. And it can interact with individuals of either type. So we might imagine a scenario where we have individuals that could be A's or B's, and they're interacting with other individuals that could be A's or B's. And maybe when an A interacts with an A, they get little a. And then the other possibilities, let's say we call them B, C, and D. So what we've written here is the fitness that results from individual interactions between individuals in terms of what types of individuals are interacting. So this top row represents the fitness of individuals of type A if they interact with a type A or a type B. And we've seen this before. This is a symmetric game that we've written here. One thing you might want to think about is, why did I say it's symmetric? Why is it important that the game is symmetric? You don't have to answer that right now, but keep it in the back of your head and think it through. It's interesting and kind of an important result, and we'll be talking about things related to this in the next videos. So instead of just having a single FA, now maybe what we want is to say that FA is maybe the average fitness or payoff of A's in the population, and FB would be the average fitness or payoff of B's in the population. So what we've implicitly put together here is the idea that there are many interactions that occur over the lifespan of an individual, and those the aggregate of all of those creates an average fitness. Also note that when we're talking about average fitness or average payoff, we're kind of talking about expected utility here, where utility is now the reproductive fitness of an individual. So we can work out what FA and FB are, because we know the frequencies of the different types in the population. The frequency of A types is X, and the frequency of B types is 1 minus X. So if we want to know the fitness of A types, it's just the payoff or fitness of interacting with an A type times the probability of interacting with an A type, or the frequency of those interactions, plus the same thing for interacting with B types. Here's the payoff for interacting with B types, and this is the frequency of those interactions. And similarly, the average fitness of B's would have to be C times X plus D times 1 minus X. Now, recall that we solved for the equilibrium, or the equilibria. We found them at x equals 0, x equals 1, or when FA equals FB. When that first came up, I said, well, that's not a very likely thing to occur just by chance. But now FA and FB aren't constants anymore. So as we change x, FA is changing and FB is changing. And there's no reason to think that they shouldn't cross at some point, so they probably are going to be equal to each other at some point. In fact, they have to be almost certainly at some point. So now there may be another equilibrium, a third equilibrium, and let's call it X star. To solve for it, we just set FA equal to FB, and we work through the math to figure out what X is, and we will find that it's D minus B divided by A minus C plus D minus B. Oops. That's X star equals that. Now, look at that equation closely. Have you seen this somewhere before? In particular, I'll give you a hint. Look back to your mixed Nash equilibria lecture. What do you see there? So what we found here is that there could be a third equilibrium at X star, but of course it's only really meaningful if it's in the range of 0 to 1, which we define as an interior equilibrium. Interior meaning it's got a frequency that's not zero or smaller than 0, and it's not bigger than 1 or even equal to 1. So it's somewhere between those two limits. It's possible mathematically that we would get a result where X star is bigger than 1 or smaller than 0, but that means they're not meaningful results because X needs to be a frequency, so a fraction of the population. This term here, interior equilibrium, we'll probably use that repeatedly in the course, so keep it in your mind. Now, if there is this third equilibrium, then the figures that we've drawn above, these two figures, aren't quite right. Or at least they don't tell the full story, because they only tell the story where there's only two equilibria in our range from 0 to 1. So those are still possibilities, but there's now two more possibilities, and we should sketch those out. So I'll just set them up here. So one possibility is that the curve, it still has to start at 0, and then it increases, but now it has to cross somewhere between 0 and 1, so it has to start coming back down, and now it's crossed and it has to come back to 0 because that's another equilibrium at X equals 1. So that's a possibility. And this would be then X star, which doesn't have to be a half, it can be anywhere. That's one possibility. The other possibility is that it starts in the negative. So it goes down like this, and then it crosses, and it crosses again. So those are the two other possibilities that can occur if X star is between 0 and 1. What you should do now is try to figure out the stability of these the equilibria. Now you see that there are three equilibria in each of these cases. There's one at X equals 0, there's one in between, and one at X equals 1. And the same thing goes for the right-hand curve here. So figure that out. See if you can work out what the stability is and the direction that the X will change, and from that, which are the stable and which are the unstable equilibria. Let me just emphasize that you will get one or the other, depending on the parameters that you're using for your game. And those, with the other two figures we drew before, form all four possible kinds of behaviors that can, or dynamics that can occur in these kinds of 2x2 games, 2x2 symmetric games in evolution. Okay, we're getting near the end now. There's just a couple last things I want to bring up. One of them is the replicator equation. So what we did is we derived the equation says the rate of change of the frequency, x, is equal to x times 1 minus x times fa minus fb, where these FAs and FBs depend on the structure of the population, how many A's there are and how many B's. So it's the frequency of A's times the payout A plus frequency of B's times the payout little b, and the fitness of B types is X times C plus 1 minus x times d. Okay, that's what we figured out from our model. Now, I want you to think a little bit about the average fitness of the population. Let's call it F bar. So can you think how you would calculate that? If we have our fitnesses of A types and average fitness of A types and average fitness of B types, then to figure out the average fitness of the whole population, we just weight those by their frequency in the population. So X is the frequency of A types times the average fitness of those A types plus 1 minus X, which is the frequency of B types, times the average fitness of those B types. Now, the interesting thing here is that the equation we wrote above for dx dt can be rewritten as x times fa minus f bar. That's kind of cool. And this is called the replicator equation. We're going to use that term quite a bit, so keep in mind that's what we're talking about. We also sometimes will get sloppy and say the replicator equation is this form up here. Both are okay in this special case where there are only two types, and so it's a 2x2 game. But the general idea is that the rate of change of x is proportional to x times the average fitness of that one type relative to the average fitness of the whole population. So what it says is that the frequency of A's increases if the average fitness of A's is above average, meaning the average for the whole population. And on the other hand, the frequency of B's increases if the fitness of B on average is above the whole population average fitness. And this formulation, the replicator equation, or this one, is going to be the foundation of everything we do in evolutionary game theory in this course. And so that's why we want to go through this derivation and build it up fairly carefully. So before we wrap things up, I just have a few closing thoughts. We've talked a lot about evolution, built up an evolutionary model. We threw in some game theory to create an evolutionary game theoretic model. And the question is, how does an individual choose between its strategies? Because don't you need that for a game? We might imagine a bacterium. How does it choose between the strategies A and B? And hopefully you already understand this. I just want to drive it home. It doesn't. The bacterium doesn't make any choices. It is genetically determined to be one of these types, either A or B. That's programmed into its genotype. And the game is played on the level of the population. And it just determines which type becomes more frequent in the population. So there's no choice of the individuals in this case. And so what happens is selection determines whether this bacterium's descendants thrive, whether they become more or less frequent in the population. And the other closing thought that I want you to take away is, why did I make a point that this was a symmetric game? We're going to touch on this later, but you should start thinking about it. And I'll give you a hint. Try to think about what an asymmetric game would mean biologically. In the symmetric game, the idea we had is that we randomly sample individuals, and so maybe we pick one individual, then we pick another individual, and they interact, play a game, and get some payoff from that. And if we do that over and over again over each individual's lifetime, then they get an average payoff or an average fitness. And that becomes the average fitness of the type A's and the type B's. What would you have to change about that kind of process or that sampling to have an asymmetric game? Okay, I'll leave you with that thought. You can mull it over and see what you make of it. You're welcome to talk to me or Christoph about it if you have some ideas. Right now, let's just summarize what we did. So first, we built a simple population model. Then we added evolution into it. We solved the dynamics, by which I mean we found the equilibria and their stability. Then we added game theory. And in the end, we arrived at the replicator equation. Maybe let me just go back a little small step. This connection here between dx dt equals this, x1 minus x fa minus fb, and this second form, x times fa minus f bar, isn't really hard to make. And I should have emphasized that earlier. But as an exercise, you should solve it for yourself and show for yourself that this is true. And I think the easiest way to do that would be to simply plug in f bar, this form of it, right in here in this equation, and check that you recover this equation here. I think that would be a valuable exercise, so you should try that for yourself. Okay, that's all we've got for this lecture. Thanks for watching.